Here we have two pictures of crystalline substances. I forget the name of this one, but that's a snowflake. That's water. Crystalline solids have long-range order to their atoms or molecules, and they are often found in beautiful geometric shapes because of the structural patterns that are present on the atomic and molecular levels. So these crystals growing with these particular geometry is a reflection of the geometry with which the molecules solidify. And the six-sided snowflake has to do with how water molecules align when they freeze. X-ray crystallography is a way to look at how the different atoms and molecules are arranged. So we learned that electromagnetic waves can interact with each other, called interference. So if the two waves are in phase, they'll react constructively, and if they are out of phase, they'll react destructively. And we also saw that light passing through two slits, where the distance is similar to the wavelength, produced an interference pattern. So we can make use of this to explore the structure of atoms, but we need something where the wavelength of the electromagnetic radiation is close to the size, the distance between the atoms. So those spacings in the crystals are about 100 picometers, which corresponds to electromagnetic radiation that we call X-rays. So you can essentially do a double slit experiment using a crystalline solid as the slit. An X-ray source, and you focus a narrow beam of that onto your crystalline solid, and as the electromagnetic radiation goes through that solid, it produces a diffraction pattern. The diffraction pattern depends on the angle at which it's coming in and how these different atoms are arranged, the spacings between the planes of atoms. So if you have two waves that are in phase, they're going to have constructive interference if the difference in the path lengths is an integral number of wavelengths. So this wave coming in hits this atom, and this one is coming in and hitting this atom. They're both going back out. There's a distance that the ray 2 travels that's farther than ray 1 because it went into the substance. And so that path difference is 2a. It's a little hard to see here, but here's a. So this distance and then back out again. That's the difference in the path. So you see constructive interference, you'll see an increase in signal when the distance is a multiple of the wavelength. So there's a whole bunch of geometry in here, but it comes down to this, which is known as Bragg's law. N, that's that integer number, n times the wavelength is equal to 2d sine of theta, where theta is this angle of incidence and d is the distance between the layers. And so by varying the angle at which the X-ray hits the solid and observing the diffraction pattern, you can find the distance between the particles. You can imagine there's a lot of math and geometry involved in that. It takes a bit of study to get much information out of something like this. This would be an X-ray crystallograph. I don't know. I shouldn't have even started that sentence. So typically what you do is you vary the angle until you find one that produces constructive interference. You measure that angle, and then you can calculate the distance between the layers. You know the wavelength, and you're measuring theta, and n could be any integer. So X-ray crystallography can be used to determine the structure of simple atomic lattices. the structures of proteins. This was very important in the discovery of the double helix structure of DNA. X-ray crystallography had a big part in that. So here's a problem using Bragg's law. The spacing between layers of molybdenum atoms is 157 picometers. Calculate the angle at which 154 picometer X-rays produce a maximum reflection for n equals 1. So, well, let's do it this way. D was equal to n lambda over 2 sine of theta. Did I get that right? D equals n lambda over 2 sine theta. So what are these numbers that they're giving us? What's 157 picometers? Yeah, that would be D, the spacing between the layers of the atoms. What's 154 picometers? Theta is an angle. That's the wavelength of the X-rays. And they tell us that n equals 1. So we're calculating the angle. The angle is theta. So we could rearrange this and get the sine of theta is equal to n lambda over 2 times d. We have n, lambda, and d, so we can get a number for that. So n is 1, lambda is 154 picometers, 2 is 2, and d is 157 picometers. The picometers cancel out, so we don't need to do any unit converting there. So 154 divided by 2 divided by 157. So that equals 0.49044506. Way too many sig figs, but when you've got logarithms and or trig functions, more digits is better. So that equals sine of theta. Sine, like natural log, is a function. It's not a thing. You can't divide by sine. You can do the opposite of sine, right? You can do an inverse sine. So if we do an inverse sine of both sides, and we have theta equals this, come on. So I'm going to use that inverse sine button and put in 0.4904456 equals, and I'm getting 29 point a bunch of stuff. Here's where we could round things off a little bit. And we're not going to get into sig figs here, but just kind of reasonable number of digits. 29.4, and the unit there would be degrees. It is important on your calculator to make sure that you haven't accidentally switched into radians or grads in your backpack. You know, buttons get pushed. It needs to be in degrees. Any questions?